Hey everyone, Mike here with the Sysadmin School. So hubs, switches, and routers. What's the difference? Most of you may know the difference, but I want to take you through a little evolution of networking and how we went from 10-base-2 networks to the networks we have today. Now, I'm not going to get super detailed here, just a very high-level overview, and this is the type of information that you may see on a Network Plus or a CCENT test. To help this explanation, I'm incorporating some animations to allow you to visualize what exactly happens. Now, please bear with me because I am not an animator, but I certainly hope to get better, and I think these visualizations really help in terms of showing you how these different network pieces of these different network equipments work. So let's start right in with 10-base-2. Now, if you've not heard of 10-base-2, don't worry. It is a super old technology. It also was called CheaperNet or ThinNet because of the low cost and the thin cable that was used for the original networking media. Now, the name comes from three parts, the first being 10 for the speed, 10 megabits per second. The base for baseband signaling, and finally 2 for the approximate cable length that you could have, which was approximately 185 feet or close to 200 feet. So 10-base-2 looked like a pretty standard coaxial cable, like the one you would plug into a cable box or a cable modem. This cable went from computer to computer with no networking equipment in between, except maybe a bridge or a repeater. Sorry, not a bridge, a repeater. We'll talk about bridges later. This type of topology was called a bus topology. If your computers were more than 185 feet apart, as I mentioned, you would need a repeater to help boost that signal to get to the other computers. Now, in the image above, or the video above, you can see that we have 3 computers, all connected via 10-base-2 network. The green caps on each end are terminators. And you have to put terminators on the ends of each cable run, or else the signal would bounce back and forth along the wires. This would cause collisions with other traffic on the wire and would break all communications on your network. One other thing to point out is, with a 10-base-2 network, any single cut in the cable is going to take your entire network down. And as we start talking about some other types of networks here later, you'll understand how we've improved over that over the years. So in this first animation, we can see normal traffic going from computer A to computer C. Pretty simple here. You'll notice that computer B also gets a copy of the traffic in this type of topology. The computer will disregard the traffic because it knows it's not meant for him. We'll talk about more of the security implications of this as we discuss hubs. Now, imagine that 2 computers try to talk at the same time. Now, in that case, there would be a collision. When a collision occurs and is detected, each computer will wait a random amount of time before retransmitting their traffic. You can imagine that as you add more and more computers, then your number of collisions are going to increase over and over as you add more and more, and this is going to affect your network performance, which is one of the downfalls of 10-base-2 is as your network grew, your performance typically took a dive. So you can see the obvious flaws in 10-base-2, but at the time it was developed, it was state-of-the-art and allowed multiple computers to communicate with each other on what was a fast connection for the time. And you can imagine having 2 computers 200 feet from each other. It'd be nice to have them be able to communicate and not have to do SneakerNet, which was basically a floppy disk taken from one computer to the other to transfer files. So moving past 10-base-2, we now transition into 10-base-T. Obvious problems we saw with 10-base-2, we eventually created 10-base-T. The T in this case standing for twisted pair, which is similar to the cables that we know today, although smaller and less actual cables in them at the time. Because many buildings were already wired with twisted pair for phones, it made it a low-cost option for existing companies to implement 10-base-T. Also, because of how phone systems were wired into the buildings, 10-base-T took on more of a hub and spoke topology instead of the bus topology that 10-base-2 used. Which brings us to a first piece of networking equipment, the hub. The hub, which gets its name from the hub and spoke topology we spoke about, is a device that would sit at the center of your network. All the computers would plug into this device. Each cable from a hub to the computer could be up to 185 feet away. just like 10 base 2. However, if there was a break in a single cable, it doesn't take down the entire network, just that one computer. The hub acts like a very dumb piece of equipment, really. All it does, it just acts like the repeater. They operate at the layer 1 of the OSI model, and they really just retransmit any traffic that's come into them. So if traffic comes into port 1, it retransmits that traffic out of every other port except the port that it came in on. So let's say computer A wants to send a packet to computer C. It sends its packet to the hub receives the packet, and sends it out every port that the traffic didn't originate on. So computer B will also receive the packet meant for computer C. But like in a 10 base 2 network, computer B will disregard the packet. So you can imagine how knowing this could have some security implications. For example, if a malicious person was able to access your hub and plugged into it, they could see all of the traffic on your network that went across that hub. So again, computer A is sending a packet to computer C. Now, if our malicious person is plugged into the hub, they will get all of the communication between computer A and computer C. So while hubs are amazing advancements over 10 base 2, they still have their limitations. The entire thing is still a single collision domain, which means that you're still going to have collisions just like in the 10 base 2 network. Collisions are detected and handled pretty much the same way in 10 base 2 networks using hubs as they are in 10 base 2 networks. After a collision is detected, both computers will wait a random amount of time before resending their packets. So similar to 10 base 2 networks, as you grew your network with hubs, you also started introducing more collisions, which then introduced more latency, and your performance started again taking a dive. So now that brings us to bridges. Even expanding and connecting hubs to other hubs to accommodate more computers caused the network to slow down. This is because we continue to increase that size of our collision domain. The larger our collision domain gets, the more chances we have for collisions. When we have a collision, we then introduce, again, latency and speed problems. And this is where the bridge comes in. The bridge is a device that works at layer 2 of the OSI model. And for lack of a better word, it bridges two hubs together. The bridge would watch the traffic and keep track of which computer's MAC addresses were on each side of the bridge. This is probably better explained through my lovely animations. So again, computer A wants to send traffic to computer C. Its traffic will go to the hub and get sent out every port except the one it originated on. The traffic will go to computer B and to the bridge. The bridge will use this traffic to record computer A's MAC address in its table. Now the bridge knows that computer A is connected to port 1. However, the bridge doesn't know where computer C is, so it will send the traffic out its only other port. This traffic will go to the hub computer C is connected to, and then it will get to computer C. Now, when computer C replies to computer A, its traffic goes to the hub, which then gets sent out every port except the originating port. The traffic gets to the bridge, where the bridge then copies down computer C's MAC address in its table. The bridge also knows where computer A is and sends the traffic out port 1. The traffic then goes to the hub, gets sent out every port except the originating port, and the traffic gets to computer A. Now, in this example, we didn't really save anything by using a bridge, but as the MAC address table gets built out, we will. So since our MAC address table is almost fully populated with our machines, let's look at the last example. Computer B is going to send traffic to computer A. Computer B's packet goes to the hub, which sends the traffic out all ports except the originating port. This packet goes to computer A and the bridge. The bridge will copy down computer B's MAC address and will know that computer A is on the same port as computer B, so it's just going to drop the traffic. In this example, computer C will never see any traffic between computers A and computers B, as long as the MAC address table is populated. Now, each side of this bridge is its own collision domain. By adding in bridges, we can reduce the number of collisions by reducing a lot of unwanted traffic to the devices in our network. Continuing on with our advancements, we now have switches. Now, most switches work at what's the layer 2 layer of the OSI model. And I say most because there are some layer 3 switches that act like routers too. And we'll talk about routers here shortly, but for the purposes of this explanation, we will be working with switches at layer 2. Switches look and work very similar to hubs, except for one key factor. A switch keeps track of the MAC address of each computer connected to it like a bridge. That way, traffic is only sent to the computer that it was destined for, not every computer plugged in. It does this through the use of a MAC address table that matches each MAC address to a port. In this example, computer A wants to send traffic to computer B. Computer A sends its packet to the switch. The switch records computer A's MAC address in the table. Since the switch doesn't have a record for computer B, it will act like a hub and send the packet out every port except the originating port. When computer B replies to computer A, the switch will record computer B's MAC address and only send the traffic to port 1 because it knows that is where computer A is connected. Now, computer C wants to send traffic to computer B. Computer C sends its packet to the switch where it records computer C's MAC address in the table. The switch knows that computer B is connected to port 3, so it sends the traffic out port 3. And computer A never sees any of this traffic between computer C and computer B. Now, remember our example of the malicious person plugging into a hub? Well, the switch offers us much more protection against that. Since the MAC address table is populated, computer A and computer C can communicate and not have to worry that a malicious person will intercept their traffic. Now, you can go a lot deeper into this, but for simplicity's sake, this is what we're going to go with. Computer A and computer C can be fairly confident that their traffic's not going to get intercepted by a malicious person who has just plugged into an open port. Switches also allow us to make use of more wires, 2 for sending and 2 for receiving, which is actually called full duplex. The hubs only allowed us to do what was called half duplex, sending and receiving on the same 2 wires, which is again what caused a lot of our collisions. In a switch network, the connection from the computer to the switch is a single collision domain. So think about that for a minute. What does that actually mean? Well, it means a lot less collisions, which means a lot faster throughput. What it also means is that growing your network doesn't grow your collision domain. So growing your network is not going to impact performance because of collisions. Now I'm going to clarify that because growing your network on a completely flat network is going to give you other performance issues, but not in terms of collisions. And this also means that everyone plugged into the switch can't see everyone else's traffic, which again, huge win, a lot of unwanted traffic that computers don't need to get, and also saves you from malicious people capturing that traffic. And switches are still used everywhere today, from your home router to switches in large enterprises. You may see something out there that calls itself a hub. Most of them don't nowadays, but they really are a switch. If you take home a $50 switch from Best Buy and plug it in, you'll find that it behaves like an actual switch. It's going to have a MAC address table, and you're not going to capture traffic between everybody. Hubs are actually really hard to find. There's some good use cases for hubs now out there, but they're kind of hard to actually find real hubs. So moving on, now we'll get into routers. So routers aren't really the next evolution, but they work side by side with switches to complete an entire network. Routers work at the layer 3 of the OSI model and really work more with IP addresses than MAC addresses. In a completely flat network, all of your computers will have the same IP address scheme. Let's say 192.168.1.x, and that .x is all the different devices in your network. There are reasons that you may want to use a different scheme as well, say 192.168.2.x, for example. Separating out networks logically like this is great for performance and security practices. But since switches only work at layer 2, computers in the 192.168.1.x network and computers in the 192.168.2.x networks will not be able to talk to each other. This is where a router comes in. A router does exactly what its name implies. It routes traffic from one network to another. So let's look exactly how it does this. Here, computer A wants to talk to computer B. Now, they're both in the same network, so there's not a need for the router. The switch can handle this traffic. Easy peasy. Now, computer A wants to talk to computer D. Since computer A knows computer D is in a different network, and I'll go over maybe in another video how to explain that, but that gets a little deeper into terms of IP addressing and that kind of stuff. Again, a little too much for this video, but for this video, let's just say computer A knows that computer D is in a different network. So it's going to send its traffic to the default gateway. And we all probably are familiar with the default gateway. It's the thing you set up when you give your computer an IP address, or most likely what your router gives your computer. Your home router gives your computer. And typically it's the network that you're on, .1. So in case 192.168.1.1. Once the router receives the packet, it knows that the destination network 192.168.2.x is directly connected to port 4. So it's going to send its traffic out port 4. It's going to go to the switch. The switch is going to know computer D's MAC address, and it's going to send the traffic directly to computer D. Computer B and computer C never see any of this traffic. And this is really how modern networks work, and how we can keep modern networks a little more secure by separating the traffic. Now, routers also provide functionality like NATing or patting. You probably have heard of that. And even some basic firewall filters. But I'm going to save, again, those concepts for another video because those can get super deep again. So that's pretty much it. That is the evolution of networking in a very compact, easy form that I hope you enjoyed. We started at 10BASE-2 and moved all the way to now switches and routers, which is pretty much what you find in your networks nowadays. Now, clearly switches and routers have evolved since their original conception, but the pieces behind them, the concepts behind them and how they work hasn't changed all that much. Those foundational concepts still apply to modern modern switches and modern routers. And that's it. Thank you all for watching. Once again, I am Mike Walton with the Sysadmin School, where I try to help anyone who wants to become a sysadmin or wants to improve their knowledge about systems administration. If you enjoyed this video and you're watching it on YouTube, a like and subscribe would be greatly appreciated. And please check out my website if you're not already on it, thesysadminschool.com. Link in the description below. And everyone, I hope you have an amazing day.